So in this example, we are going to find the voltage across the capacitor when the current given in the figure here is applied to the capacitor. So initially the capacitor was charged with 2 volt. So that means VC initial, like VC at t equal to 0, is 2 volt. So assuming that we have a current source, okay, that's represented by the graph here, and let's say there's a switch that, and then we have a capacitor here that is connected to the circuit, and then at t equal to 0 we close the switch. But initially, before we close the switch, the voltage across the capacitor is 2 volt. Okay, so we wanted to find the voltage as t evolve across the capacitor. And so for question A, we're asked to find VC of t and sketch VC of t. But we know that the current IC is C dVC dt. So this implies that dVC dt equal to 1 over C IC of t. So then we have VC of t, which is 1 over C, integral from negative infinity to t, I of x dx. Now I like to write this equation. Okay, so if you watch one of my previous videos when we were dealing with the inductor, I would like to write this equation so that I can account for the initial conditions, like initial value, because this current is a piecewise function. So you probably tend to agree with me that if I have VC of t0, then it's 1 over C integral from negative infinity to t I of x dx. So the t0 here, so that means VC of 0 will be integral from negative infinity to 0 I x dx. So as you can see, VC of 0 capture everything, that all the charges that are accumulated across the capacitor over time before we flip the switch at t equal to 0. Okay, so then I could write VC of t, which is integral from 1 over C, integral from negative infinity to t0 ix dx plus 1 over C, integral from t0 to t I of x dx. So I miss C here. So V0, so 1 over C. So as you can see, this captures all the charges, right? All the voltage accumulated, all the charges. You know, there's a relationship between charge and voltage across the capacitor. So before t equal to t0, right, that's going to be the voltage, and then we wanted to find now the voltage from t0 to t I of x dx. So that's the equation that I'm going to use. So I put it in this form as indicated above to be able to account for the initial values right? Because the current here is defined as a piecewise function of time. Okay, so the next thing that I'm going to do is to find the equation of the current for each interval. So I of 0, so when t is less than 0, right, the switch is not closed, so the current I of 0, so I of t is equal to 0. Now, so let me do this properly. I'm gonna write it as a piecewise function. So I of t will be 0 for t less than 0, and it will be 15 milliamps between 0 less than t less than 3 milliseconds, and then it's negative 10 milliamp 3 milliseconds less than equal to t less than equal to, I can close or open it, doesn't really matter, less than so, well, if you like, I could just close it on the lower end, and less than t less than 5 millisecond, and it's going to be 0 when t is bigger or equal to 5 milliseconds. So that's the current. Now I wanted to compute the voltage across this capacitor over time. So I'm going to make space here to do that. So I want to find, so I know that Vc of 0 equal to 2 volt from what we were given, right? Initially there were 2 volt. Across the capacitor. Now, so what we wanted to do now is to find for the interval 0 less than equal to t less than equal to 3 milliseconds. Now, what do we do? So we know that Vc of t will be Vc of 0, right? So that's my t0. Okay, right, so this is my t0. That's t0. Okay, so then plus 1 over c integral from 0, which is my t0, to t of I of x dx. So what I need to do is to substitute the value in there. So I have 2 volt plus the capacitor value is 10 micro, so 1 over 10, so it's 1 over 10 to the negative 6 times 10, which is negative 5. Okay, so 1 over 10 to the negative 5 will be 10 to the 5, right? Integral from 0 to t, and the current is 0.015 amps dx. Okay, so when I integrate that, that gives me 2 plus 1500 t. Okay, so obviously remember T is still in millisecond. Okay, so that's the first voltage. Just calculate here now. So that's number one. Number two, we have I is negative 10 milliamps. So I can calculate that the voltage there. So VC of T, so that is 3 millisecond less than equal to T less than 5 millisecond. Okay, so that will be VC of 3 millisecond, right? So that's my T0 now, right? So this is my T0. Okay, now plus 10 to the 5, which is 1 over C, and to go from 3 millisecond to T minus 10 milliamps. So if you like, it's minus 0.001, minus 0.01, 0.01. Okay, so dx. So when I integrate that, right, so the VC of a 3 millisecond is 2 plus 1500 times like 3 millisecond, we 3 times 10 to the negative 3 plus 10 to the 5, right? So the integral of minus, so if you like, I would just multiply that, then we have minus 10 to the 3, okay, and then T minus 3 millisecond. Okay, so that will give me so I have 2 plus 45 times 10 to the negative 1, which is 4.5. So minus 1000 T. Okay, and then minus 3. So that becomes plus 3. Okay, so this is 2 plus 4.5 plus 3 minus 10 minus 1000 T. So that's 9.5 minus 1000 T. So that's the VC of T for this interval. And the last one, when T is bigger or equal to 5, then the current is 0. So IC of T is equal to 0. So in that case, you have VC of T will be VC of 5 millisecond plus 0. Okay, so that is 9.5 minus 1000 times 5, 10 to the negative 3. So that gave me 4.5, right? So 9.5 minus 4.5, which is 4.5 volt. Okay, so putting it all together, we have VC, which is 2 volt. For t less than 0, that's t equal to 0. So that's what happened before t equal to 0. So at t equal to 0, if you like, I can just put it like that. Then so to be, I can just put it like that, like 2 volt for t less than equal to 0. And then I have 2 plus 1500 t when t is between 0 less than equal to t less than equal to 3 millisecond, and then 9.5 minus 1000 t, 3 less than, that's 3 millisecond, equal to t less than equal to 5 millisecond, and then for t bigger than 5 millisecond is 4.5 volt. Okay, so we have to sketch it. Okay, just sketch this. So let's say this is 1, 2, 3, 4, 5, 6, 7. Okay, so this is 1, 2, 3, 4. So I need to move it down a little. So well, yeah. So let's say I could just do it this way. All right, so 1, 2, 3, 4, 5, 6. Well, this axis is not properly scaled, so let me scale it properly. So this will be 1, 2, 3, and 4, and 5, and so on. So before t equal to 0, so this is 2. So the voltage across the capacitor is 2 volt. Then from 2 to 3, okay, so this is 3, 4, 5, 6. So this is 6. So let's say this is 6.5. So it should go to 3, which 6.5. If you plug that in, 6.5. And then at 5, it will come down to 4.5. So 4.5 at 5, so it comes down to 4.5 and then stays there 4.5. Okay, so that's the voltage across the capacitor. So let's say this is 6.5. So here that's the voltage across the capacitor over time. Okay, so the time is a millisecond. Now, and this value is 4.5. So now we are asked to find the second question, question B. We're asked to find the energy. So the formula for the energy is 1/2 C VC square of T. So at 3 milliseconds, that's where we're asked to find it. We're asked the energy stored in the capacitor at 3 milliseconds. So the energy at 3 milliseconds so 1/2 10 to the 5. The capacitor value is 10 to the -5 rather, and VC, the voltage at so VC 3 millisecond square, so 10 to the -5 over 2 times VC, which is at 3 milliseconds, which is 6.5 square. So the energy at 3 milliseconds is when you plug that into the calculator, it should be 211.25 microjoules. Please subscribe so you don't miss any of the upcoming videos.